This video is a continuation from Complex Roots Part 1, so if you haven't watched that, I would advise you watch that first. Now, so here we are solving an equation, z to the power of 4 minus 12i equals to negative 5. So just like we do with any equation, we try and make z, or the variable, the subject. So let's start by just making z to the power of 4 the subject. Now, in this situation, if I rewrite the right-hand side in polar form, then I can apply the Math's theorem. So that's what we're going to do. Okay, so always remember to rewrite your right-hand side in polar form. Okay, so now what we need is our modulus. That's just using Pythagoras, negative 5 squared plus 12 squared, that gives you 13. And to work out the argument, I would always recommend you sketch your complex number. So minus 5 on the real axis is over here, and 12i on the imaginary axis is over here. So this is our complex number. So that's the angle we're looking for, and the radius is 13. So now we are going to use this angle here as our reference angle. So let's work out tan inverse of opposite, which is 12 over 5. Okay, so that gives me 67.38 degrees. Now, however, that's not the angle I'm looking for. I'm looking for this here, and we can see it's definitely greater than 67.38. So you can see that if we just go 180, take away the reference angle, you are going to get your argument. So argument of minus 5 plus 12i is going to be 180, take away 67.38. And that gives you 112.62. Now, there are different ways of working out the argument, and that's fine as long as you understand what you're doing. That's all that matters. Now, so let's rewrite the whole thing out. So you've got z to the power of 4 equal to 13 cis 112.62. Now we're going to write it in a more generic form. So in degrees, it's going to be 360 n. So that is the first part. Now, moving on. So we are finding z. So we're going to take fourth roots on both sides. So you'll have z equal to 13 cis 112.62 360 n to the whole power of 1 over 4. Now applying Math's theorem. So remember, if z is r cis theta, the Math's theorem says z to the power of n is r to the power of n cis n theta. So here our n is a quarter. So we've got 13 to the power of a quarter cis 112.62 plus 360 n times a quarter, which is going to be over 4. So I can write 13 to the power of a quarter as fourth root of 13. So this here is our general solution. Now what we can do is find the particular solution by substituting different integer values for n. So let's start with n equals 0. So that gives us our z1 is 28.5. just write that a bit clearer. Okay, so now let's work out what the other roots are. So let's look at n equals 1. So our z2 is going to be 4th root of 13. So it's 118.15. And we keep going. So n equals 2. And that gives me z3, which is 4th root of 13. So it's 208.15. And n equals 3. 4th root of 13, cis, doing the same thing, just changing that n to z4, 4th root of 13, cis, 298.15. Now, these angles are not in principal argument form, so they have to be in the range of negative 180 to positive 180, and they're not. So we'll look at how to rewrite them in our principal argument form. So if you just draw your angle, 208 is about here somewhere. So we are looking at the other side, and we know it's going to be negative. This one's positive. Now, this angle here is 208.15. So I can, all I'm doing here is going 360 take away 208.15 and then negative of that. So in other words, it's actually going to be, if I simplify that, it's 208.15 take away 360, which gives me negative 151.85. Okay, similarly, so I'm just going to go straight away 298.15 take away 360. And there we have it. So I've got my roots in principal argument form as well. So I can try, and there we go. So I've got all my 4 roots, Z1, Z2, Z3, and Z4. Okay, so now let's look at the next type of problem. So here we're finding 5th roots of 32k to the power 5i. So first we're going to write out the equation. So we've got z to the power 5 equals to 32k to the power 5i. Now we want to write the right hand side in polar form. So what we want to do is, just to give you an idea of what's going on here, there is no real part. You've only got 32k to the power 5i. So this is 32k to the power 5i. So the modulus is 32k to the power 5. And the argument we can see is 90 degrees. So let's work in radians, and it's going to be pi over 2. So now that we have those two things, we can write it in polar form, and we'll write it more generally. Okay, now I'm going to simplify the argument a little bit. So write it as a single fraction. So pi plus 4 pi n over 2. Okay, Now, so the next part is we want to make sure, just like what we've done in the previous question, we want to work out for different values of n what the answer is going to be. But before we do that, we're going to apply de Moivre's theorem. So z is taking fifth roots on both sides. I've got this. So that to the power of 1 over 5 is going to give me 2k. And I'm multiplying the argument by 1 over 5, which gives me pi plus 4 pi n over 10. So this here is my general solution. Now I'm going to substitute different values of n to work out the particular solutions. So let's start with n equals 0. So z will be 2k cis pi over 10. Okay, so that's my z1. So for n equals 1, I get 2k cis pi plus, pi plus 4 pi over 10, which gives me 2k cis pi over 2. Okay, so I'm going to quickly give you, instead of showing you the substitution, I'll give you the final result, 2k cis 9 pi over 10 z to the power of, when n equals 3, we will have 2k cis 13 pi over 10. And when n equals 4, (17 pi over 10). Now, not all of these answers are in principal argument form, and the way to figure it out is if the fraction is greater than 1, you know it's not in principal argument form. So this one and this one are not. So applying what we just did with the last one, again, because this is in radians, I'll be taking away 2 pi. I will get 2k cis negative 7 pi over 10 for this one. And with this one, I will get 2k cis negative 3 pi over 10. Okay, there we have it. So if you have any questions, please email your teacher or leave a comment below.